students, welcome to my class. Today we will study water and all the properties of water and about the hard water and soft water, and all those topics that I am going to do today are introduction, definitely, physical properties, universal solvent, solution, hydrated substances, soft and hard water. And I will see that I will follow your syllabus so that it is better for you. And let's not waste our time and begin with the introductory part. So water, the formula as you all know, H2O, the chemical name dihydrogen oxide, the molecular mass 18. You all know the first chapter of language of chemistry we had done how to calculate molecular mass, like hydrogen's atomic mass is 1, 2 hydrogens, so 2 into 1 plus oxygen 16, and that is equal to 18. As you all know, it exists in 3 physical states, solid, liquid and gas, and it is the major constituent of all living being. It supports the life. Without it, life is not possible for all living being. How important it is. And the total amount of water on Earth's surface, as you all know, is 70%. But out of that entire 70%, only 2.5%, which is very little, 2.5% of water is fresh for use, and only 1% is accessible because rest is frozen in the ice caps and in the polar region. So just imagine how little water is there available for us for drinking purpose and etc. Therefore we should always conserve water and avoid wasting it. And the scientists, they had a major role playing, giving us what is water and how it is prepared and all. So the famous scientist Henry Cavendish synthesized water from its elements. That is, he ignited 2 volumes of hydrogen and 1 volume of oxygen. And further, Lavoisier confirmed that water is a compound. Earlier, water was not taken as a compound many years ago. Anyway, so these are all the general about water which you all know, and just to revise it. Now let's straight away come to the physical properties. Pure water, that is when we are talking about H2O, distilled water we say. So pure water is colorless, odorless and tasteless liquid. And pure water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. But this temperature at which it boils, that is boiling point, and the temperature at which it freezes, that is the freezing point, will increase with pressure. Like when pressure is increased, boiling point increases and freezing point decreases. Means this temperature will be more than 100 degrees Celsius and this temperature will be less than 0 degrees Celsius. And the same happens, means boiling point increases and freezing point decreases with dissolved impurities. I will explain with increase in pressure. Like suppose you go to the hill stations, the hilly region, the pressure decreases. There the water will boil at a temperature less than 100 degree and it is difficult to cook because the water is boiling at a temperature less than 100 degrees. So less temperature, less heat energy. At the same time, when you use a pressure cooker, it will always increase the pressure. So when it increases the pressure, now the water will boil at a temperature more than 100 degrees Celsius and the food is cooked better. Now I come to dissolved impurities. Like normally we say add salt, common salt, sodium chloride is added to bring a cooling effect. The reason is that on dissolving impurities, the freezing point decreases. That means the temperature is less than 0 degrees Celsius. So the ice will melt, but it will melt not at 0 degree, it will be at less than 0 degree, thereby not increasing the temperature further unless the entire mass of solid melts. Thus, it gives a cooling effect. Very important, you will get question from here definitely. So, see that you can answer it well. Next, anomalous expansion. Water contracts on cooling, but between 4 degree to 0 degree. I will repeat myself. Anomalous expansion means that behavior which is different from the rest. Like the rest, matter expands on heating and contracts on cooling. So does water expands on heating, contracts on cooling. But the water, when the temperature comes to 4 degree to 0 degree, it will not contract, it will expand. This is the anomalous expansion. So, due to this, when it expands, the density will definitely be less. Thus, ice has low density than water. So, the aquatic life survive. How is that possible? When in the cooler region, the water starts cooling from 10 maybe to 8 to 5, then to 4. As it comes to 4, water will expand, become lighter, stay at the top, come to 0 degree. It will freeze, and the density being lower, it will float on water, and the lower part of the water body does not freeze. Thus, the aquatic life survives. And it is seen that the density of water is 1 gram per centimeter cube at 4 degrees Celsius. Why at 4 degrees Celsius? Because it is maximum at this temperature. Beyond it, expansion takes place. Very important definition, as I had told you earlier also, children. Please see that the definitions are learned from the text. And children, if you are following, please like, share and subscribe my channel. Now next, the lakes and rivers do not solidify easily. You have seen this. It's a natural process. Lakes and rivers do not solidify easily on account of high specific latent heat of solidification. I will explain this. And another phenomenon that you see, steam causes more serious burns than boiling water on account of high specific latent heat of vaporization. Another thing, due to high specific heat capacity, water is able to modify the climate or used as coolant in car radiator. So there are 3 things that we are seeing, that lakes and rivers do not solidify easily. People get burnt due to steam more seriously than when boiling water falls on hand. And water is always used as a coolant. Now let me tell you what is specific latent heat of solidification or specific latent heat of fusion. It is the amount of heat required by ice to change into water is latent heat of fusion without any change in temperature. Now what happens whenever, this you have done it in the junior classes as well, state changes, interconversion of states, solid to liquid, liquid to gas, gas to liquid, liquid to gas, where you used heat energy. Even to increase the temperature, you are using heat energy. When you heat something, the temperature rises. But whenever there is a state change, solid to liquid or liquid to gas, it is only the state change which is taking place due to the heat energy supplied. There is no increase in temperature. Now, this is the amount of heat energy required by the ice to change into water, and is known as the latent heat of fusion without any change in temperature, and its specific value is 336 joules per gram or 80 calorie per gram, and the same amount of energy is released when 1 gram of water solidifies to form 1 gram of ice at 0 degree Celsius. So this is what is happening. Now when I talk about the latent heat of vaporization, the amount of heat energy required to change water into vapor without any change in temperature, again liquid is getting converted into gaseous state, is known as the latent heat of vaporization, and its specific heat is high, 2268 joules per gram or 540 calorie per gram, which is very big amount. And when we come to why water is used as a coolant in car radiator, due to high specific heat capacity, and specific heat capacity is the amount of heat absorbed by 1 gram of water to increase the temperature by 1 degree Celsius. For example, if the water is at 20 degrees Celsius, to increase it into 21 degrees Celsius, the amount of heat required is known as the specific heat capacity. So we go to the next slide. We will now talk about water as a universal solvent. That is, water dissolves many substances forming aqueous solution. The reason is water is a polar covalent compound exhibiting charge separation. Actually, when we talk about water, the bond that is there is oxygen having 2 single bonds with 2 hydrogen. This is a covalent bond, single covalent, and it's polar in nature. Why? Because oxygen is more electronegative than hydrogen, thereby exhibiting a charge separation. At the same time, water has high dielectric constant, due to which it reduces the strong electrostatic force of attraction between the cation and anion of an ionic compound. For example, if sodium chloride is added to water, sodium chloride is one ionic bond which has a ionic bond between sodium and chlorine. Sodium is the cation, chlorine is the anion. So the sodium and chloride ions are attracted together in the ionic bond with a strong electrostatic force of attraction. And due to water's property, high dielectric constant, this force of attraction is reduced, weakened. Thereby, it can mix properly with the help of this polar covalent, that is exhibiting charge separation. Then we come to water can even dissolve glass. Due to this universal solvent, it even dissolves glass, but in very small amount. Thereby, it leaves etching on the inner surface of the glass vessel. Means, if you can have a glass vessel and put some water in it and leave it undisturbed for a quite long time, you can see marks in the inner surface of the glass vessel, which is known as etching, as water can even dissolve glass. Then the next, they dissolve salts and minerals are necessary for the growth and development of plants and animals, and also adds taste. So till now we were talking about pure water as it is shown in the previous slide, pure water. So when we drink pure water, it has got no taste. But the salts and minerals, when are added, it adds taste. Along with that, it has importance for the growth and development in the plants as well as animals. Important, okay? Then we say universal solvent, even gases dissolve in it. All kinds of substances, most of them are dissolved in water. So does gases. But among gases also, oxygen is more soluble than nitrogen, because in the air nitrogen is present mostly, but while dissolving, oxygen is more soluble than nitrogen, and therefore it helps the aquatic life of both plants and animals. Therefore, it is difficult to find pure water in nature. So there are so many points which you can you can add it up and write a beautiful answer. Why can't we find pure water in nature? So the next slide. And the next topic is solution, that is homogeneous solution. When we say solution, we are talking about homogeneous solution, which is a mixture of solids in water, and solid is a solute and water the solvent. This you know, it is not new to you. So when we say homogeneous solution, because just now we were talking about water as a universal solvent, that means it can dissolve many things, and here we are talking about solids in water. A true solution, it's a clear, transparent, homogeneous mixture with a size of solute about 10 to the power minus 10 meter, very little, very small. And also it cannot scatter light, it cannot be filtered, it cannot be seen as well. So a true solution. And the solution that is made out of the solid in water can be saturated, can be unsaturated, can be supersaturated. So a solution which cannot dissolve any more solute is saturated, which can dissolve solute is saturated, and a supersaturated solution is mixing of solute on increasing the temperature. I'll explain. Suppose you have a glass of water and you add 1 spoon of sugar to it, and then you add another spoon of sugar to it and stir it. That becomes one unsaturated because it can still dissolve half a more spoon of sugar in it. When you add 1 spoon of sugar to that unsaturated, you'll see small granules, small crystals of sugar on the bottom of the vessel, stating that the solution has become saturated. If that solution is heated a little, you will see that you can dissolve even 1 more or 1.5 more spoon of sugar into the solution, making the solution super crystal, which is known as crystallization, which I am going to discuss in the next slide. So when water is a solvent, it is known as aqueous solution. When other than water, like petrol, alcohol, acetone, many other solvents are there, that they are known as non-aqueous solution, and the one specifically which is alcohol is a tincture. So these 3, aqueous solution, non-aqueous solution and tincture, you should be able to identify. Children, I am repeating it once again. Please learn the definition from your text and go by the syllabus. Okay. Now next, solubility. That means just now we were talking about 1 spoon, 2 spoons, saturated, unsaturated. But when we talk about calculation or exactness, we can't say about 1 spoon. There is a measure. So solubility, how much? When we say more solute, how much? So that's solubility. It is the amount of solute that dissolves in 100 gram of a solvent to form a saturated solution at that temperature. So depends upon temperature. More temperature, more solute. Less temperature, less solute. So amount of solute which makes it saturated at that temperature is the solubility, but the amount of solvent is also needed, that is 100 gram. Now when we talk about solubility, there are 3 more factors. One is temperature, which I discussed just now, stirring and size of solute. I will explain. Suppose you take a glass of water and you add 1 spoon of sugar crystal, and in another glass of water you take 1 spoon of powdered sugar. Definitely the powdered sugar will dissolve faster. If you are doing with constant stirring, even then the solubility is faster. If you are doing with increase in temperature, even then the solubility is more. So these are the 3 factors which alter the solubility. Then solubility curve. Children, this is important. It's a line graph that plots changes in solubility of a solute in a solvent against changing temperature. So you can draw a graph of the solubility of a solute in a solvent against temperature. Now here the solubility is shown with many different salts like potassium nitrate, sodium nitrate, potassium bromide, sodium chloride, potassium chloride, and so on. And you see each line graph will tell you their solubility. Like if you talk about sodium chloride, the solubility increases, but it is very little, very little, very little. When we talk about potassium nitrate, it increases, but it increases at a very less temperature and too high. Whereas potassium bromide, potassium sulfate, they will increase. Even potassium nitrate, they will increase, but will have a gradual trend of increasing. Whereas if we talk about calcium sulfate, it increases and then after a particular temperature it decreases down. The same with the global salt, it increases and then it decreases. Such a solubility is known as anomalous solubility. This is global salt which first increases and then decreases. You need to know about the trend of solubility of each of the salts. Children, you need to remember them. Very important, this both the graphs. There's one Henry's law. the scientist, the great scientist Henry, he stated the law. So Henry's law states that at a given temperature, the mass of gas dissolved in a fixed volume of liquid is directly proportional to pressure on the surface. For example, soda water, you all have seen. You can see the fizz out when you open the cap of the bottle. Why? You're releasing the pressure, so the gases are definitely thrown out and it comes out in the form of bubbles. So mass of gas dissolved by a fixed volume is directly proportional to pressure. More pressure, more gas dissolved, less pressure, less gases dissolved. Okay, so we go to the next slide. Okay, a crystal, important and very interesting. And let me tell you, children, you need to remember, you are definitely going to get questions from here. Definitions, you are going to get the examples, reasoning questions, and I am going to explain all of them. So a crystal, as I told you just now, crystallization from a supersaturated solution. So a crystal is a homogeneous solid with definite geometrical shape. Some of them I have written it down: sodium chloride cubic, learn it children, copper sulfate rhombohedric, ferrous sulfate octahedral, potassium nitrate prismatic. So some are there, there will be some more in your text, please learn them. Hydrated salts, when during the process of crystallization, when a crystal is formed, when the salt is thrown out in the form of crystal, some of the salt will contain certain water molecules in it, which is known as water of crystallization, due to which it gets a color. Like ruby has got a red color, copper sulfate has got a blue color. These are all due to those water of crystallization contained in it. So some hydrated salts, the crystals of some salts contain water of crystallization. For example, blue vitriol, Epsom salt, white vitriol, potash, aluminum gypsum. These are some of the crystals which may or may not have color, but they have certain water of crystallization. I would suggest, please learn the chemical name, the common name and the formula of all those salts mentioned in your text in this particular chapter. So we come to anhydrous. When it is a hydrated, it can be anhydrous also. Anhydra means the salt lacking the water of crystallization, which is removed by heating. When you heat the salt, the water is lost and that becomes anhydrous substances. At the same time, there are some salts, some crystalline substances which do not contain the water of crystallization, like common salt, nitre, sugar, potassium permanganate. There are many more in your text, children. Please learn the common name, the chemical name and the formulae. There are some salts which decrepitates. What is decrepitation? Like on heating sodium chloride, it produces a crackling sound. How? Why? Because the big crystals break into smaller one. This crackling sound is known as decrepitation. I give you one question. What do you observe on heating blue vitriol? So this was discussed in the earlier video. You will get it in your text as well, or if you can remember, try to answer. If you have doubt, please put it in the comment section. I will clear them all, and all these notes will be there in your description box. So whenever you are preparing, go through it. Now we go to the next topic, that is efflorescence, deliquescence, hygroscopy, drying, dehydrating agent. Now what is efflorescence? When a particular salt or a compound is kept exposed to the atmosphere, it loses the water of crystallization, that is the crystalline changes to powdery or amorphous, and some of the examples are washing soda, Globus salt and Epsom salt. As I said, learn the formula. Then deliquescence. This is a phenomena by which when the substance is kept exposed to the atmosphere, it will absorb water, or that is moisture, from the atmosphere and convert into a saturated solution. And the examples are caustic soda, caustic potash, magnesium chloride, zinc chloride, calcium chloride, ferric chloride. But we can also see that when table salt is exposed to the air, it turns moist. Though table salt is not deliquescent, then how is it happening? Actually what happens, the salt which we get in the market, that is the commercial use one, it has got magnesium chloride and calcium chloride mixed in it, and both of them are deliquescent in nature. Due to this nature, they absorb water, and thus sodium chloride also is soluble and it turns moist. Next, hygroscopy. This substance also, when exposed to air, will absorb moisture, but it will not change into the saturated solution. The examples are Kong sulfuric acid, phosphorus pentoxide, and quicklime. The next is drying agent. Some substances are used to remove the water from the substance without any chemical change. So Kong sulfuric acid, phosphorus pentoxide, quicklime, silica gel. Dehydrating, it will also absorb water from the substance, but it will chemically take it out, and the best example is concentrated sulfuric acid. I give you one more question here. What do you absorb on heating niter? Try to answer. Okay, so the next topic is soft and hard water. Water that forms lather with soap easily is a soft water, where some of the water do not lather easily, and that is hard water. So soft water is easy and good to use. It has got sodium salt dissolved in it, so it is safe to use. But the hard water, which does not lather easily with soap, has got a reason. And what is it that makes it hard? Therefore, we know that the bicarbonates, chlorides and sulfates of calcium and magnesium, that is calcium sulfate, calcium chloride, calcium bicarbonate, or magnesium sulfate, magnesium chloride, magnesium bicarbonate, presence of any one of these 6 salts makes it hard. So the hardness also are of 2 types. One is temporary hard water, another is permanent hard water. If it is calcium bicarbonate or magnesium bicarbonate, the water is temporary hard. And if it is calcium chloride or calcium sulfate or magnesium chloride or magnesium sulfate, it is a permanent hardness. So the reason for temporary hardness of water and permanent hardness of water are presence of these salts. How to remove it? The removal of temporary hardness can be done by 3 ways, that is by heating, by adding lime, or by washing soda. So by heating, that is by boiling, calcium bicarbonate, which is water soluble, will give you calcium carbonate, water and carbon dioxide, and calcium carbonate is a precipitate which can be filtered. So can be done for magnesium bicarbonate as well, to give you magnesium carbonate, water and carbon dioxide, which comes out as a precipitate and can be filtered. The removal can also be possible with lime, that is calcium hydroxide. So to get calcium carbonate and water, again precipitate, filtered. If in case of using lime, if magnesium bicarbonate is used, then you get magnesium bicarbonate, calcium carbonate and water, and both the precipitates can be filtered out. And one more method is by using washing soda, that is sodium carbonate. So you get calcium carbonate and sodium bicarbonate, and the precipitate is filtered out. As I said, the soft water is the one which lather easily. It contains sodium salt, which is safe to use. Then we have the method to use remove permanent hardness, that is also by using soda ash, that is washing soda. So sodium carbonate, and that will give you calcium carbonate and sodium sulfate. Though for removing magnesium sulfate, a little lime has to be used, because magnesium carbonate precipitates are little difficult to remove. So that is what is all about soft and hard water, the reason for the hardness, the method to remove heating. There are many more equations in your text showing you the heating of magnesium bicarbonate, showing you magnesium bicarbonate with lime. Please practice them all. See that you balance the equation whenever you write it, and the advantages and disadvantages, which you had done it last year, but still it is there point wise in your text, so do learn it. And as I had said, please learn the definitions that's given in your text, go by the syllabus, and let me show you. I have done almost all the topics that I had taken here: physical properties, universal solvent, about solution, crystals, crystallization, hydrated salts, efflorescence, deliquescence, soft and hard water, and I have tried my level best to make it simple for you to understand. So please hit the like button, share and subscribe my channel. Do hit the bell icon to get notified about my upcoming video. Thank you, children.